Alright, today we're going to be talking about logarithmic functions. So to start off, we'll start with just saying, let's talk about a function being 1 to 1. A function f is said to be 1 to 1 if the range value corresponds to exactly one domain value. So let's contrast two different functions and which one is 1 to 1 and which one is not 1 to 1. So these are two that we have seen so far, with this being an exponential function and this being a parabola. And we can see that if you can almost think about like a horizontal line test, that if each range value corresponds to at most one domain value. So that is saying that each horizontal line that we can draw on this graph should cut through our function at most one time. So that's what it means with saying each range value corresponds to exactly one domain value. Contrast that with the parabola that we got going on over here. We can see that for for some horizontal lines, we can see that horizontal lines will cut through this function more than one time. So for some range values, so range equals to 10 maybe right here, we can see at the range value 10, there are two domain values that will give that range value. So this is not 1 to 1. So how can we use that? Is that we can say that if f is 1 to 1, then the inverse, that's what we're going to be interested in, the inverse of f is formed by exchanging the independent and dependent variables for f. So if we typically say like y equals a function of x, all we're going to be doing is exchanging the x and y values. So if x1 comma y1 is in f of x, then if we exchange the y values with the x values, then y1 comma x1 is in the inverse. So what we're doing, we're going to be exchanging the y values and x values is what we're doing when we are talking about the inverse. So let's go over a visual example where we might have the function y equals to 2 raised to the x. That is a nice exponential function that we have been dealing with so far. If we wanted to exchange, and this is a 1 to 1 function, if we wanted to do the inverse of this function, that would be y equals, now here's a new term, log 2 of x. And we can see that we're almost like flipping the original graph along the line y equals x, and that's what we are doing. Alright. Now, like we alluded to talking about the log, I want to start talking about logs. So the inverse of an exponential function is a logarithmic function. Logarithmic function. So, like we have stated, we have the equation y equals to 5 raised to the x. So that's going to look like a function like that, where the domain of this function is going to be all real numbers. The range of this is going to be from 0 to infinity, not including 0. The inverse of this will be log base 5 to the x equals y. If we graph this, it looks something like that. And the range and the domain are going to flip this time for us. So the domain, rather than being all real numbers, it is going to be from 0 to infinity. And the range, rather than being from 0 to infinity, is going to be all real numbers. Alright, so let's go over some examples of dealing logs. So they can be kind of tricky. It's not exactly intuitive. So, examples of logs. Alright, so if we have log base 5 of 25 equals to 2, well, that is the same thing as saying the base 5 raised to the second power equals to 25. Let's do another example. Log base 9 of 3 equals to 1/2. Or we would say that 9 raised to the 1/2 power equals 3. Or if we have log base 2 of 1/4 equals -2, or that's the same thing as saying 2 raised to the -2 power equals to 1/4. Alright, let's do it in the other direction now. So if we have 4 raised to the third power equals 64, well, that's the same thing as saying log base 4 of 64 equals 3. If we have the square root of 36 equals 6, well, that's the same thing as saying log base 36 of 6 equals to 1/2. Or if we have 2 raised to the -3rd power equals 1/8, well, that's similar to saying log base 2 1/8 equals to -3. Alright, so now we're going to get into properties of logarithmic functions, things that we're going to have to be working with. So properties of logs. Alright, number 1. If we have log base b of m times m, well, that is going to be the same thing as log base b times m plus log base b n. So the log of a product is the sum of the logs. 2. Log base b of m divided by n is going to be log base b m minus log base b n. So a log of a ratio is going to be the difference in logs. 3. Log base b of m raised to the p power. Well, that is the same thing as saying p times log base b of m. So we can, this is going to be a property that we especially are going to be using a lot, is that when we have a log of something being raised to a power, we can take the log of the whole thing and be able to pull out that power. Alright. Last property that we're going to be dealing with, if we say if log base b of m equals to log base b of n, well, then we know that m equals n. Alright. An important note that we keep talking about log base b. A lot of times that we are going to be interested in log of e, and this is what we call the natural log. Or we say the ln, natural log. And we are going to be using this a lot when we are going to be working with logarithms, when we're trying to solve for variables when we have equations that use an exponent. So let's use natural log in an example. So let's do a money example that we've been talking about. So let's say, how long will it take to double my money if R equals 20% and we are compounding once a year, and M equals to 1. So we don't have a continuously compounding equation. We have a setup where we are compounding at set intervals. We're compounding once a year. So we are going to be using this A equals to P times 1 plus R divided by M raised to the MT. And now the question is saying, how long will it take? So we want to solve for this M right here. And we are asking how long will it take for our money to double. So remember, A is going to be the amount of money that we have at the very end, and P is going to be our initial investment. So if we are thinking about how long it will take for our money to double, then we know that A will equal to 2P. We just want to double the initial investment. And we know that this R right here is going to equal to 0.2. So we can start plugging in some information into this equation right here. So we have 2P equals to P times 1 plus 0.2 divided by 1, all raised to the 1 times T. And we want to solve for that T. So what we can do right off the back is that we can divide both sides of this equation by P to get rid of these annoying P's. And we are going to have 2 equals to, I'm going to simplify the interior of this parentheses right now. So 0.2 divided by 1 is just 0.2. 1 plus 0.2, we are going to get 1.2 times raised to the single t, because 1 times t. And now we want to solve for t. And how can we solve for that t when it's up in the exponents? That we are going to want to, what I call, pull that exponent down out in front. And let's go back to our original property dealing with number 3. Is that we can take the log, or in this case we can take the natural log of both sides of the equation in order to pull an exponent out from the exponent. So we can say the natural log of 2 equals to the natural log of 1.2 raised to the t power. So all we did was took the natural log of both sides. And now that we have taken a log to both sides, well, we can take this exponent and pull it out front. So we're going to get natural log of 2 equals to t times natural log of 1.2. And now we can divide both sides by the natural log of 1.2. So we're going to get the natural log of 2 divided by the natural log of 1.2, and that equals to t. And we can plug in the natural log of 2 divided by natural log of 1.2 into our calculator, and we are going to get about 3.8 equals t. So how long will it take for our money to double in an account that compounds once a year at interest rate 20%? Well, it's going to take about 3.8 years. Alright, let's do another example when an account is continuously compounding. And in an account, so this is another example, in an account that continuously compounds, what interest rate will turn $5,000 into $7,000, let's put dollar signs there, in 4 years? That might be a question we might be interested in. So we have $5,000 to invest. We know that at the end of 4 years that we're going to want our money to be $7,000, and we might be interested in what interest rate do I got to earn to be able to turn $5,000 into $7,000. So because we are dealing with continuously compounding equation, we are going to be using the equation A equals to P E raised to the RT. Some people like to say A equals to PERT. I find that a little funny. Alright, so we are going to be looking into what are we going to plug in. So we're going to, $7,000 is going to be our A, our $5,000 is going to be our P, $4,000 is going to be our T, and we're going to want to solve for that R. So we're going to have 7,000 equals to 5,000 E to the R times 4. Alright, so first what we're going to want to do is divide both sides by 5,000 to get that E to the RT all by itself on the right hand side of the equation. And we are going to get, what is it, 1.4 equals to the E to the 4R. And now we are going to want to pull this exponent down out front. So just like in the last example where we took the natural log of both sides to pull the exponent down towards the front, we're going to do the same thing again. So the natural log of the left hand side of the equation equals to the natural log of the right hand side of the equation. Now that we have the natural log of E raised to the 4R, we can now pull that 4R out front. So we're going to get the natural log of 1.4 equals to the 4R times the natural log of E. Now, the natural log of E, because E is the natural log is the inverse of E, we know that the natural log of E equals to 1. So that's a nice property that we're going to utilize here. So we are going to substitute that natural log of E equals to 1. And we're simply just going to get natural log of 1.4 equals 4R. Now we can just divide both sides of the equation. Well, we can plug in natural log of 1.4 first into our calculator, and we're going to get 0.34 equals to 4R. Divide both sides by 4, and we are going to get 0.09 equals to R, or R equals to 9%. So what do we do in this equation? Remember, the very beginning of the question was saying, hey, what interest rate do we need in order to turn $7,000 or turn $5,000 into $7,000 in 4 years' time? And by plugging in 7,000 for A, 5,000 for P, 4 for R, 4 for T, and then we are solving for R. When we solve for R, we're going to get 9%. And that is telling us that our account that we make our investment in has to be 9%. An annual interest rate of 9%. Alright, well that concludes today's lessons.